Hello, I'm glad to share with you today a short presentation on some graphical item analyses using non-parametric curves. The goal today is to be very practical, practically minded, be able to help you develop some skills and look at some of the advantages of using conventional item analysis methods, as well as some graphical non-parametric curves. I want to highlight at the beginning that what I am introducing as graphical nonparametric curves are fairly easy to use. They're intuitive, they've got some value, but there are more efficient ways of doing this using graphical nonparametric item response theory. Today, however, it's really aimed at folks who are doing more conventional, what we might call classical test theory, item analysis, and moving people toward approaches using continuum of variation. All right, so let's start up. So today I'm going to talk about item analysis, and as we all know, hopefully at this point, that item analyses can be used in the test development process and test revision, and to even later understand why a test shows specific levels of reliability and even validity. The aim is to have approaches that inform the whole design, development, administration, potentially down the road, revision of a test. Historically, a great deal of development in item analysis has focused on knowledge tests or aptitude tests, but mostly knowledge tests, and on quantitative statistical indicators of item characteristics that help us make claims about an item's quality, so that whether it's a good or bad item, or whether we should retain it or revise it, using some combination of information about an item's difficulty, discrimination, and guessing. Today, we're going to talk mostly about psychosocial measures. An example I'm going to show you is with an instrument that's used in basically it's a measure of depressive symptomatology, a self-report measure. So it's not a knowledge test. So difficulty, we're going to have to redefine what difficulty means. We'll talk some more about this in a bit, but you can get a sense of this as we'll go through. Traditionally, for knowledge exams, today we're mostly going to focus on psychosocial exams, and I'm going to use exams or tests, but really these are instruments or measures. So we wish to get an intuition for the characteristics of good or bad tests and good and bad test items. Items are the building blocks of assessments and tests. And therefore, you could have a very unusual situation in which one or two bad items are in fact balanced out by the preponderance of very good items. But for the most part, I think it's sufficient to say that bad items lead to bad tests or bad assessments. So a good test should differentiate, discriminate among test takers who have very little, a moderate amount, and a lot of the intended attribute we wish to measure. Little highlight here is that the way we're going to think about it here, the way the scoring goes, is that the higher the test score, this implies the higher the amount of the intended attribute we wish to measure. So good items should differentiate among low, moderate, and high test takers. That's really about this discrimination of the item. We're going to talk about difficulty and how we're going to reconceptualize difficulty in these sorts of items that we're going to look at today. And it's going to come right out of these graphical approaches. And of course, lower asymptotes and potentially even higher asymptotes. Well, in today's world where we almost have, the aim for many organizations is anytime, anywhere testing and on-demand testing, but nonetheless, the dominant model it continues. You have, test takers in a variety of environments. They could be at home, they could be in a test center. They could be in a large testing setting. We involve cloud-based. These are the encounters, the test-taking encounter. It's the interaction of test takers with items. And I've been writing in my own research about this idea. And what's interesting is almost in every case, we end up, these interactions, these encounters are scored item by item, and then they end up being in a data file, flat data file. Here's just a sample. And based on that data file, we calculate some numerical, single numerical indices of item difficulty, things like p-values, and item total correlations. A p-value is really an item as an average item score if it's binary, meaning if the items are scored 0, 1, then the average is a p-value. It's traditionally classical test theory, which is the item difficulty. But the average of the item as a concept actually is informative on its own. So p-value is the average of binary items. And we look at things like item discrimination, which are typically in a classical test theory or some sort of item total correlations, or we'll see in a bit, sort of corrected item total correlations. There's other indices, but again, they really are coming down to one or maybe two numerical summaries. And the theme today is that a numerical summary is not a bad place to start, but it's not enough to make the kinds of decisions that we need, and that the graphical approach as a supplement to all of this, I think, is going to give us a great deal of information. And it'll prepare us to think about test theory models that involve this scatter plot kind of idea. Don't worry, we're going to get there in a few minutes. So the aim today, and a lot of the work that I've been doing, is to put the psychology back in psychometrics. So I want to really see if we can use some data visualization, some graphical approaches, even the most rudimentary ones, to describe the encounter of a person, a test taker, survey respondent, and an item or task. That encounter, that is then scored in some way. And as I said earlier, or just a moment ago, the sort of dominant approach is then that score is entered into a sort of a flat file. This could be a spreadsheet or something like this. And every cell, right? This is person 1 for item 1, person 1, item 2, person 1, item 3. That's the basis of almost all of the psychometric analyses that we do. And we usually end up, and I have contributed to this in my own work over the last 30 plus years, on looking at things like item difficulty, discrimination, through very simple indices involving means, correlations, covariances, etc. So our goal today is to motivate analysis through the lens of describing the encounter by at least adding at the beginning at least one more dimension, this continuum of variation. We'll continue to use statistical ideas and concepts, but as much as possible, we're going to rely on a description of the item analysis tools using a psychological motivation and data visualization graphs to give us a sense of these concepts of item difficulty and discrimination. The scatter plot of an item and test scores will be the backbone of the data visualization. In fact, that scatter plot, where on the x-axis is some representation of the score on the test or the instrument, and that's the x-axis, and the y-axis is a score on the item. So the item and the whole test. That is the backbone to a lot of this. So the example I want to use is this, I think it's called the Centers for Epidemiology Scale of Depression. It's a 20-item scale introduced by Radloff and colleagues, and you'll see a bit more details. And it's shown to be useful in clinical and psychiatric settings, although it's not really intended for diagnostic purposes. I'm not a clinician, but it is important to sort of bring that up here at the beginning, I think. But rather is an index of current feelings of general depression, as my colleagues who are specialists in this will say, something called depressive symptomatology. It's a very busy slide. You can take a look at it, but what the individuals are instructed to respond to each of these questions, thinking back in the last week. And, the kind of questions we're going to work with today that are very interesting is number 17. Item 17 is I had crying spells. This is the original CES-D. I mean, and basically, how often have you cried in the last 7 days? And you respond either 0, 1, 2, or 3, depending if it's not even 1 day. Or 1, that'd be a 0. A 1 if it's 1 or 2 days. 2 if it's 3 to 4 days, or 3 if it's 5 to 7 days. It was developed and introduced in 1977 by Radloff in the Journal of Applied Psychological Measurement. Sample I'm going to look at here is 600. It's a subsample of a larger study, 600 adults, and that from data that was collected in Canada. Couple points to note as well is items 4, 8, 12, and 16 need to be what's called reverse coded. So you'll see item 1, like item 1, I was bothered by things that usually don't bother me. I don't feel like eating. My appetite was poor. I felt like I could not shake off the blues. Then the 4th was, and I feel that I was as good as other people. Well, clearly that this item has a valence that's opposite. It's talking, if you were to give a 3 here, that's actually a very positive encounter, in particular we're thinking about depressive symptomatology, so you would reverse code it. So a 3 becomes a 0, right? Right, so you would just simply go back and a 0 become a 3, 2, etc. So you would reverse code it. And items 4, 8, 12, and 16 are just like it. For example, item 16, I enjoyed life. It's a measure of depressive symptomatology. You will want to reverse score those items. So the key point here is that the composite, that is the scale score, is not depression itself or even depressive symptomatology, but rather is an observable indicator of the level of depression. Or actually, the score is an indicator of depressive symptoms. If you go back here, you'll see that these are very different kinds of depressive symptoms, right? My sleep, felt fearful, thought of my life, I thought my life has been a failure, etc. Those are sort of depressive symptoms, the symptomatology. So the score is actually not depression. Depression is really the phenomena, the attributes. People might refer to a construct. But we now have an item response. You get a total score over the items, right? You add up, you reverse score, then you add them up. That total score is actually an indicator of a variable of interest. And then you go from that total score to some phenomena. This first bridge from the sum of the total scores to an underlying variable, that's sort of step 1, stage 1, and that involves like data quality, reliability of measurement, and then the second step, which is from the latent variable, for example, a true score in classical test theory or in test theory or universe score, in generalizability theory, or a factor score in factor analysis, or a theta score in IRT. Those are all latent variable scores. You get a prediction on those scores, and then from there, you would make some claims about the attribute. The first step from the items to the latent variable, it's a lot about data quality. It really is about error of measurement. That's the main driver, not the only one, of course, but a main driver. And then the second stage really is where validity goes in from the underlying variable to claims about the phenomenon. So the CES-D, as we saw already, prompts the respondent to reflect upon his or her last week and respond to questions such as, my sleep was restless, and then to respond either 0, 1, 2, or 3, whether it's not even 1 day, 1 to 2 days, 3 to 4 days, or 5 to 7. All right. Composite scores then, if there's 20 items and they range from 0 to 3, the total score is the possible range is from 0 to 60, because each of the items is 0 to 3, and there's 20 items. All right. A general review is presented of a selected number of psychometric analyses. There's other ones that are out there today. I'm going to be very selective to contribute to the evidential basis of the quality of the test scores, that first stage computed from the responses, right? Understanding that encounter, that interaction. So my highlight is going to be on classical test theory and begin to move us ahead to novel graphical approaches with an eye towards even becoming more efficient as you progress in your development and learning in psychometric theory. This is a sample here that actually was gathered in northern British Columbia. It's part of a larger survey. I have 600 respondents, 290 of them identified as female. The average age was 42, and 310 identified as male with an average age of 46. So this is a community sample. It's a community dwelling sample. It's not a clinical sample. It's a community dwelling sample. This becomes important because in a community dwelling sample, that distribution, you're not likely to my understanding, not likely to get a lot of individuals who score very high. So it's fully anticipated that I expect to see a skew in our total scores where they're all bunched up towards the bottom because it's a community sample. If this were a clinical sample, it would be the other way around, where there would be a lot more at the top. Let's see if that hypothesis or hunch holds out. All right. I don't think we need to say too much more here. I think you've seen a lot of this. Here's a snapshot of the data file, of what a data file looks like. These are 8 respondents. First 20 columns are the responses of the 20 items of the CES-D scored or rescored for items 4, 8, 12, and 16 in a 0, 1, 2, 3 format. We then add those up and you get what's called the observed total score. We have, in this data file, it's called sex, it's gender, it's male and female. You'll see in a moment the coding, right? Females coded as 1. So in row 1 is a female coded, sex was coded as 1, who's 43 years old, and their CES-D score is 16 out of 60 points. So as you can see, they had a lot of zeros across, a couple of 1s and 2s, out of 16. So if you add those up across that top row, it gets to be a total score of 16, an observed total score. And I did a little distribution here for you of the age. You can see that there's 600 individuals. The scores on the CES-D range from 0 to 50. There's no one who gave us a score larger than 50. Are we surprised? Not what I said a moment ago, because it's a community, is a community sample. It was done through a survey, a larger survey, social survey. So the CES-D, they really do bunch up towards the bottom. This is going to become important. It's going into the data to get a psychological understanding. Is this a meaningful representation? It is. Most people will actually score quite low here. And the age of the individuals, that's their distribution there. So the basic building block of what I want to talk about is this scatter plot. And a scatter plot, if you haven't seen one already, I hope you have, is a type of data display that shows the relationship between, in this case, 2 numerical variables. Each member of the data set gets plotted as a point in the XY coordinates. So every one of these points, in this case, could be 1 or more depending on the shading of individuals. And describing scatter plots, we look for form or shape and trend, direction, strength, outliers, etc. And that graph, this is actually a very powerful tool, because if we can get our head understanding through a scatter diagram, where in a few minutes you'll see the CES-D score will actually be on the x-axis, and as you'll see in a few minutes, the item responses are on y. This is actually just a scatter plot of the CES-D and age. I don't see much of a relationship there at all. It really hasn't. There might be a small correlation, but look at all the variability and look at the uncertainty here. Right? Again, there's not a lot of information up here. All right, let's look at the item analysis, the focus on graphs and data visualization rather than just an overall number. I think it's worthwhile to see what would be at least one display, the very simplest, most common display of item analysis in sort of a classical test theory. You'll see for item 1, the average score, even though it's 0 to 3, the mean score was 0.483, standard deviation 0.749, and what's called the item rest correlation. So it's the correlation of the score on item 1 and what's called the rest. It's basically partialing out that, or removing the studied item out of the total score. You'll see there's situations where I do that and situations where I don't, depending on the purpose of the analysis. But in the classical sort of, this is a fairly standard index that's used, that's the number, that is the discrimination, and that is the difficulty of this item. Typically, we don't do too much with the standard deviation, although there is a item reliability kind of statistic you can get, which is involves a product of some of these numbers. But typically, it just gives a sense of the variability for that item across the 600 individuals. What we look at is the mean. If this were a binary item, this would be a p-value. Of course, some items, see the average here for item 11 is 1.02, but the correlation of that item and the CES-D score removing item 11. So we're looking at item 11, so it's 0.50, right? That for that item. What was that item? Item 11. Item 11 was my sleep was restless. So you'll see that it's not too surprising that if we're thinking about restless sleep, it's probably going to be a little higher than something like item 9, which is an item that I thought my life had been a failure. Well, it's not too surprising in a community dwelling sample where the proportion of depressive individuals with high depressive symptomatology is not going to be high on this instrument, right, in a community dwelling sample. And so what we see here is that, yeah, look at that. Yeah, sure, that makes sense. Meaning the average is going to be lower compared to item 11. So the mean of the item scores is a proxy for item difficulty, and the item rest correlation, or what you'll sometimes hear called the partial, item total, the corrected item total correlation, item rest correlation, that's a proxy for the discrimination. And so the item rest correlation, sometimes called the corrected item total correlation, is the Pearson correlation, assuming a linear relationship, of the scores on the item and the total score of the studied item, well, of the total score with the studied item removed. So let me try that again. It's the Pearson correlation, meaning the linear relationship of the scores on the item and the total score with the studied item removed out of the total score. So all of the item rest correlations are positive. That's a very good sign. If one was negative, there's a variety of reasons one could be negative. Typically, it's because we haven't recoded an item. Like, if item 4 were negative, we'd say, oh yeah, that's right, we have to go back and recode it. And then the correlation would become positive so that a high score on the item reflects greater amounts of depressive symptomatology. You can also get a negative one just because you have a really terrible item. Well, it does happen. In my experience, that's less often, but certainly the fact that they're all positive is a good sign. And a larger correlation is good, but what do we learn from this? We really don't learn too much, in my opinion. And this follows the trend in statistics that we need to move beyond just single numerical value summaries. Well, here is a scatter plot, a linear scatter plot. We saw this is item 1. So you see the CES-D score on the x-axis. You see this is the overall score, but that's the whole score. I did not remove the item 1 out of it. This is the whole score. I left that. So basically, there's a little bit of a double count. Not terribly alarming. There are 20 items, so I wouldn't worry about it too much in this case. But it makes it easier to interpret in this, for the moment. But this is the linear correlation. It's 0.578. You can see it's not too surprising at 0.5. It's going to be close to a diagonal. These dots are the respondents, someone who gave a 2 and a total score of, well, actually a 10 and a 1. There's probably more than one individuals in there. I want to highlight 20 here because if you look at it, and we're going to see in a moment in the statistical analysis, it begins to trail off the number. This is the density plot for the CES-D score. There's not a lot of people after 20. There's some, of course, and there's no one beyond 50. So if you just focus on this range, I just use this to help us guide our eyes. Item 1 is actually an interesting item that way. It really is. It shows the things that I look for. It starts down here, increases. There's no flat. There's no point in which you get, in a sense, a reversal of the monotonicity. This is the linear relationship there. And what this is what's called the lowest smooth response curve. If we go back to the linear relationship, which is really this item, not item rest, but the item rest correlation is 0.578, but this is the correlation with the total score. What's interesting in this is that's the number, and this is the graph of that number. Assuming that it's linear, the item had a mean of 0.483, and a median, that is the 50th percentile, was actually 0. So at least half of the individuals responded 0 to this item on a 0, 1, 2, 3 scale. Even doing this actually gives us a lot of information about the encounter that resulted in the scores. There's a lot more we've got to do, but it's quite interesting. I took it a step further and said, well, why do we need to force it to be a linear relationship? Why don't we, in a sense, use a non-parametric curve that I'm going to describe and let the curve determine the data to help inform the location of that curve of that line. Again, when the relationship kind of looks kind of linear still. If you look at these two graphs, it's hard to tell. There's not a massive difference between them here. There is some, and we'll see more about this in a few minutes. So in a sense, one can say that the linear relationship, the Pearson correlation, does reflect it very well. And you see the pattern is about the same here, that individuals who have, this is an interesting way to think about it. This curve is a curve that tells us what is the score, the expected score for someone who has different values of the total score. So as opposed to just having a number and we need to make some sense of it, here we say, okay, let's introduce this continuum of variation, which for now is just the total score. Just to make it simple for us, there's more modern approaches using things like test graph. Jim Ramsey, Professor Ramsey, an emeritus professor at McGill University in Canada, has developed an exciting way of doing this, but that actually has a much better X variable in here. But let's not worry about that yet. Let's get our heads into this and then move from there. But you can see that at every score, so individuals who have a 20 overall, their sort of expected score is about 1. What's interesting is you can see that as we go up, the expected score also goes up. This kind of monotonicity, that's very important. So we like to see something where it begins down here, it's going up. We can actually have an upper asymptote that we can see here. Does anyone actually even, there's not a lot of people in this area. So this gray curve, which is the confidence band, is very wide. More individuals here. So the confidence band around the non-parametric regression line is, in fact, far narrower, standard statistical thinking. But individuals who get a total score of 30, the expected score is between 1 and 2. It's about a little under 1.5. There's going to be some variability around that. So how far do people have to go before they get, you have to almost score 40 in a population before you're even going to say 2. And 2, if I remember correctly, was, well, it was, so a 0 is basically none or only 1 day, 1 or 2, and I think a 2 is 3 to 4. 3 or 4, and very few people, and there's not a lot of people up here at all. So there's that confidence band. This gives you a sense of the precision of measurement as well. All right, so I'll let you read this a bit more, but we'll see though, I'm going to say a few words. We'll use a method of fitting a smooth curve. Cleveland actually has done some beautiful work going back even long before that, and there's been other work since on fitting curves like this. Excellent work by Jim Ramsey, Ramsey and Silverman and others. Excellent work. It's a real big burgeoning area. We're going to use something called LOES. It's a shorthand for locally estimated scatterplot smoothing. There's various of these. It's one of the most flexible non-parametric regression techniques that aim to fit a smooth function. A smooth function is a function that aims to capture the general patterns in the XY variable relationship, and the result of a LOES analysis is a line through the moving central tendency of the XY relationship. So in essence, you have these little bands, you can vary the width of them. It bends up the x-axis, and then it gets a relationship, a line in there, and how it estimates the line can be a variety of techniques where you're weighting extreme scores and different kind of functions. And then, so those are kind of like, and then those points are connected to get a smooth looking line. And depending on the degree of increasing your smoothing or not, you get fewer bumps. We'll see that in a few minutes. Say a few words, give you an intuitive notion. There's actually a lovely technical literature. National Institute for Standards and Technology of the United States, I think that's the title of the organization, has a nice little link. I'll leave it for you to get there. So you can start with this bandwidth, these width of points adjacent to the point being predicted, and some sort of low degree polynomials, a very common way of doing it, is fit through the subset. You can control the weight given to points closest to the value that you're predicting in these little slices. The resulting equation is then used to predict the value of the selected point for that bin. And then the data are shifted 1 over, and this continues as it goes along the value of the range of the x-axis. And then those resulting points are connected to fit a line. I'm going to show you in a few moments, we're going to try with this live data looking at SPSS. I'm also going to show you using an R package through the Jamovi interface, but we'll do it with SPSS as well. And we're going to use I'm going to keep it the simplest way possible. It's just to use the sort of legacy displays. You'll see the scatter diagram. It'll create that scatter diagram. I'm going to show you how to then get a fitted line. And we're going to use the LOES. And I'll tell you in a few minutes what kind of kernel I prefer. There's a whole bunch of them, as you saw here a moment ago, that SPSS gives, and if you use other packages, they give you even more. The Gaussian kernel for the normal distribution is a very common one. The two that come up here is I'm actually going to get us to use the tri-weight. Data close to the current point receive higher weights than any other kernel allows, and extreme cases get very little weight. So you're getting down weighting of extreme cases. It's like a robust estimate, and there of some sorts are more sturdy to extreme scores. So I'm going to recommend with SPSS that we use the tri-weight. Some programs won't give you that option, and you need to be some caution in how you do this. Be careful. There's a lot of concerns with using these kinds of graphs. They are not a panacea. Great place to start. You're going to learn a lot about ideas that'll actually become very helpful as you become more sophisticated over the years in the kinds of analyses as you move to things like item response theory and other approaches. So many of the concepts like where is the data bunched up is going to become very relevant. And is there enough information? And is it possible that as you slice up your bin, you could actually end up with very little data? So you might have to do a wider bin, etc. I'll leave this up here. These are the steps. You're actually going to see them visually in a moment in SPSS, and you can pause this video and follow that if you need to. All right, let me now switch over to SPSS. Here is SPSS, this data. I've only kept it to two items, item 17 and item 18. I just want to highlight here that in SPSS, it allows these to be sort of ordinal, right? Actually, a sec should actually be, well, let's leave it as ordinal, but actually one could even put that as binary. SPSS is not too fussy about that. But this is what the data look like here. And I'm just going to hide some of the controls here. The way I do it, so you can see it, is go to Legacy Dialog, Simple Scatter Plot. I can reset it, but let's take a look at, let's take a look at item 17. I'm going to put the overall score there on the x-axis. And for the moment, let's just go here. I'm hoping you can all see me still as I switch graphs in SPSS. I hope you can all follow me. And so here, what I typically would do then is double click on the graph. You'll see it come up. And then I'll go to Elements. I'm going to fit the line. And I'm going to use the low S smooth. Well, that's what the linear looks like. Here, I'm going to do the low S smoothing. I'm going to use the tri-weight. It doesn't do confidence intervals very well, so I'm not going to worry about that. And you'll actually be able to see it in a moment. There it is. It's a lot of fuzziness. There's a lot of movement. It's bumping up and down here a great deal. Let me show you what it looks like if I did a different kernel. See, that one smooths it out a little bit in there. Smoothness is not the only, it's a variance, bias variance trade-off and such that we worry about. Here is the the one for with the tri-weight in here. What's interesting is if you increase percentage of points of data points to fit, if you increase that to something like 90%, look at that. Look at that. You can now see there's a lot more smoothing out with the tri-weight. And if you went down to something like 30% or even 20%, you're going to see this sort of percent of the point almost gives you a sense of the bandwidth a little bit in that way. And so you can see a lot more fuzziness. So one has to be careful. I mean, there's sensitivity. You need to look at these graphs carefully. What's interesting is if we stayed with the with this kernel here, and let's say we did 90%, Look at that there. You can still see, you can see some consistent patterns, and you'll begin to play with it a bit more with SPSS in there. This is a very interesting graph from here. You can then hit close, put the X, and now you've got it. You can transport it. You can export it like you would with any, you can export it to PDF or to a graph and paste it in. But what you're getting here is this idea that into the 20s, it kind of stops into that range there. That's for item 17. Item 17 is during the past week, I had crying spells. Interesting. Can we try something different here with this one? Let's try a new one. And I'm going to show you one more, a scatterplot, which is actually kind of fascinating. Let's do the same thing, except now let's put the male-female marker in there so that we can now designate whether someone is identifies as male or female. Female are the blue dots, male is the green. Now it's interesting. Look at this. What we might kind of, again, if we go to here, sorry, let me make sure that we're still on the same, good, we are on the same page. If I double click on the graph, I go to elements. Now I can fit a line at subgroups. Now that's the straight line. Fascinating. I'm not going to go with the straight line. Let's close it. It's hard once you do the straight line to get rid of it. So I typically like to go back, rerun the plot again, go to elements, fit it for subgroups, low S. Let's leave it at this particular kernel. Look at that. Pattern is very odd. You're seeing for female respondents, they're actually more likely to endorse the item than male respondents. Let me change the weight coefficient here a little bit. Oh, look at this. Look at this. Look what this graph tells us. And for those of you who know a little bit about psychometrics and item analysis, this is a variation on a kind of diff analysis. It's a bit of a naughty graph. SPSS is not the best software. It's a good place to start, but not the best software to do this. But you can now compare, like even at 20, individuals who identified as male typically would select a 0, and individual respondents who identified as female tend to respond more with a higher score, right? That's fascinating. Even at a 30, take a look at this. At 30, there's almost a 1-point difference. This is interesting. One needs to unpack this, bringing in the psychological theory to unpack it. But what we've really done is we've introduced this continuum of variation into item analysis. And I think that's really important. I think that's very cool. I think that's the way we need to start. And that's the first step towards item response theory, non-parametric or parametric, item response theory, Roche modeling, or whatever you wish to do. It's the injection of that continuum of variation. Cool. One last chart. Let's do the same chart, but let's actually look at item 20 rather than at item 17. Look at that. This item is during the past week. I could not get going. And look at this. Fit it for subgroups. Let's do the, if you leave it linear, they're almost the same. In fact, the one way of thinking about this is that the item total or correct item total correlation is the same, would be the same for individuals, the subgroups, subsamples of individuals who identified as female, individuals who identified as male. If we move it to a non-parametric regression, and again, very close, very, very, very close. I would say that for this item, there's little to no differential item functioning or bias, that the two subgroups are performing very much the same. The curves are very, very close when they're on the same graph, as opposed to the crying item. There's actually a paper by Mikla Gellin and I in, 2005 in the Journal Educational Psychological Measurement, where we did this even more thoroughly in this item and showed that actually this item is quite problematic. And it could actually lead to overall test scores that, it's a question. If individuals who identify as female are scoring higher overall, is it due to the fact that some items like this, where if you match males and females and the level of what you're measuring, there's actually a difference in how the items function. Very interesting idea. I'm going to do one last changeover and then we're done with the video. Let's switch over now to Jamovi. Switch over to Jamovi. Jamovi is, for those of you who don't know, runs R underneath. And so this is really an interface for R. So we're now going to use R basically to do the analysis to get a little bit more flexibility. So it's the same data file that we brought over here, just so that you know, for R, in most cases, you have to make sure that the item is listed as continuous, because Jamovi's kind of quirky about that. So a couple ways of doing it. One way is very simple, even just using the basic, the basic R package, right? If you saw where I was here, I went to exploratory scatterplot. Well, CES-D goes in the x-axis, item 17 there. Let's group it this way. You could do the linear one. This is for item 17, right? This is the crying item. I don't like that linear relationship. If you look at it, it's not persuasive to you. Look at this. There it is. I can add standard errors around. Ours a much better. Jamovi. It's a very simple little interface. Look at that, right from there. You can see the data points. I wish we could control these a bit more. And if you get better at R coding, Jamovi's a nice interface. It's kind of like a sort of a start in on it. And you're seeing, again, the same thing, right? A respondent who identifies female. Look at the difference. There's like a 1 point difference. Look at that here. Look at in this area higher up. So this is not irrelevant. The width of these this tells you these confidence bands. Nice thing about this package is you can actually also include, making it a bit more fuzzy, complicated to look at, but this is the distribution of the CES-D for female and for male. So you'll see that they're actually matching. Here the matching is not as good because female respondents are higher on it. Now, we'd have to, there's some sophistication you have to get into because this is the total score and has this item in it. So we'd probably want to remove it here. And here is the scores, the plots for the actual item. So these are the two axes, if you wish. These are the density plots. You could replace it with box plots instead. For those of you who like box plots, there's that instead. Yeah, interesting to see this one. The box plot here for male respondents is really, there's little to no variation there that we can see. You can sort of take a look at it here as well. That's one way of doing it. There's a much nicer way of doing it, frankly. I use FlexPlot. FlexPlot is kind of cool. The outcome variable, let's take a look at that same item. The predictor is the CES-D. So there it is, just overall. Very nice. I made some of my graphs that way. You can see the uncertainty around the line. If you want to break it down by you put that in there, and look at that. It did it automatically. Very clever little piece of software where you can see, again, the same kind of patterns that you have here. SPSS is kind of interesting. It actually gives you more control than the Jamovi interface does in terms of this. But there's once you get into R and you're programming, Jamovi, again, this is a great way of getting involved in this. Wonderful. And what I like here is that you can see, you can, by injecting this continuum of variation into the problem, we're actually getting a great deal of explanatory power, trying to understand, the gender differences with this item. This item is the I feel blue item. Can I try something here that I think is cool? Or at least I think it's cool. Rather than the overall score, let's turn this, let me use what's called the component score. What the component is, I took all the items and I just wanted to have a cheap, quick, dirty little latent variable. And so I did a component analysis, saved the factor score, component score, with 1, so it's an overall. It's a little bit, it's highly correlated, just so that you'll see there is a high correlation, as you can expect, between the total score and the component score, right? That correlation is 0.994. Not too surprising. In fact, for those of you who are my friends who do things like item response theory, it's that the total score and the theta from IRT actually is also that high, just a little bit lower in a lot of the models. But look at this, it's a flexible, this is not technically a perfect IRT because there isn't a simultaneous, the efficiency isn't great here, and there's a little bit of sloppiness. But as a graphical tool to get you thinking in this way, when you enter the continuum of variation, these are Z-scores. These are Z-scores. So almost everyone, look at that. You see? These are Z-scores. They are no longer total scores the way we had before. If you put the total score in instead, there it is here. This is helpful because this is actually in the units of the score there. Thank you very much, and I hope you enjoyed it. Take care.